Okay, in this video we are going to be moving on to our fifth module. Our fifth module is going to be uniform circular motion, and everything we're going to be talking about in this module corresponds to stuff that's discussed in chapter 6 of the text. Okay, so uniform circular motion is the simplest form of curved motion. It is motion in a circular path at some constant angular speed. And we'll sort of see how that plays out here as we define some terms. So we're going to want to define a number of different variables that we're going to use to discuss this type of motion. And maybe the first thing we can do is take a look at some of these diagrams. I've pre-drawn some stuff on this PDF here, so we can discuss some of these things more quickly. So we can imagine, well, what are we doing here? We're talking about things that are moving along a circular path. So it doesn't have to be the full disk here, but we can imagine that some object starts at this point on our circle, and after some amount of time it moves over to here, right? The most convenient way to maybe describe that motion is by discussing circular motion, right? And so if we want to do that, we need some tools. So the first tool that we're going to want to talk about is probably just the idea of angle, right? So imagine instead our object started over here, and without loss of generality, we can usually rotate these problems so that our object does start at 0 if that's necessary. So if we label this spot theta 0, and we just call that 0, and then this thing rotates up to the point over here where it ends up at theta final. Let's say as I do in the example over here, let's say we call that theta final pi over 4 radians, okay? And we're going to talk about radians a little more in a second. But if this object goes through this rotation, then we define the rotation angle, or delta theta, to be this quantity here. It'll be theta final minus theta initial, okay? And I'm going to erase this stuff here to clean up the notes. But basically we want to be thinking of delta theta as just being our final angle minus our initial angle, right? And whenever we talk about angles in this context, we want to be talking about angles in radians, not degrees. So what are radians? Most of you have probably seen radians before, but basically there are 2 pi radians in a circle, so 2 pi radians makes 1 full revolution, which is equal to 360 degrees, as we can see over here, right? And so if 2 pi radians is 360 degrees, then 1 radian would be something like 57.3 degrees. But you won't really have to worry too much about this conversion that you see here, because we're basically going to want to be working in radians the whole time we're talking about uniform circular motion, okay? And maybe sometimes you're going to want to convert back if you have to state the answer to a problem or something in terms of degrees, but you can always use this conversion to make that translation back to degrees, okay? So now that we have our delta theta, which is our rotation angle, we're going to want to also define what arc length is. Okay, so we give arc length the symbol delta s here, and arc length is just the distance traced out by this circular motion at a distance r. So it's actually the length of this curved line here. Okay. And so we want some way to relate delta theta to delta s, right? So again, our delta theta, our rotation angle, to delta s, which is our arc length. So we want to be able to relate the two. If we start from the equation of a circle, so c, which is the equation, we can then very quickly see what the relation will be, right? So if the full arc length of the full circle is 2 pi r, we can take only part of that, right? So in this case here, we only want part of the arc length of the circle. So if we only want part of that, well, how much of it do we want? Well, we want whatever delta theta is over 2 pi, right? We want some portion out of that 2 pi. And so if we multiply both the left and the right of our circumference equation here by delta theta over 2 pi, we get the equation that we see here. And then we can clean things up a little bit. You can see on the right-hand side here, I've canceled the two 2 pi terms. And on the left, well, what is delta theta over 2 pi times the circumference? Well, that's just the part of the circumference that we want. And the part of the circumference that we want is delta s. So all of this here just ends up being delta s, right? So if we clean this up, we end up with delta s is equal to r delta theta. And that is the expression for our arc length in terms of our rotation angle. It's just arc length equals radius times rotation angle. Okay, we're going to define a couple more terms, and then we're going to look at, or a couple more variables, I should say, and then we're going to look at a quick example. Okay, so here we define angular velocity. Angular velocity is given this symbol omega. This is a Greek symbol omega, lowercase omega. And what is it? Well, it's defined as a timed rate of change of the angle, right? So it's just the timed rate of change of our delta theta. So it's delta theta over delta t. And this is always measured in SI units in radians per second, right? So before our delta theta was measured in radians, right? And it was just the change in that angle. And now we're interested in the change in that angle. Well, over what time period did that happen? That's our delta t. And so this is going to come out to be in radians per second. You can see here I've drawn this little diagram where we have our delta theta, so our change in angle. And if this happened over some time period delta t, well, the angular velocity of this object that was rotating would be given by omega equals delta theta over delta t. Okay. And one last term that we want to be defining, this is the tangential velocity. Your text calls this the linear velocity, and this is just the velocity of the actual edge of the circle as it rotates. Okay, so we can think of this as the instantaneous velocity that say a fly or a bug sitting on the edge of the disk would feel. So you can imagine if there was a fly sitting on the edge of the disk here, what would it feel that the instantaneous velocity was? What would it feel that v was here? And that is the velocity that we're talking about here. We're also going to look at an example of this on the next page here. But so we can kind of see that well, this velocity would have to be delta s over delta t. This is just our arc length, the changing of our arc length over time, right? And so we see that here represented in this equation. So we're going to want to use that equation as well. But maybe a more useful version, or a more useful way to state what our tangential velocity is to realize that that we also have this expression for our arc length, right? We can write our arc length in terms of the radius and our rotation angle. So if we do that here, we take this and we rewrite it using this expression over here. We end up with the expression that we have down here. And we can clean this up because we know that delta theta over delta t is our angular velocity, and so we get this tidy equation down here. And this one's going to be pretty useful for us. We're going to use this fairly often. Okay, and what is this saying? Well, this is telling us that our tangential velocity is just equal to our radius times our angular velocity. Okay, and remember, our tangential velocity will be written in terms of let's say in SI units in meters per second, right? So maybe I'll make a note of that here. SI units, meters per second, right? Because it's actually a distance. We're actually moving some number of meters over some number of seconds. It's not some number of degrees. That was our angular velocity. So again, our angular velocity is going to be written in terms of radians per second. Our radius is written in terms of meters, and so our tangential velocity is written in terms of meters per second. Okay. Okay, so those are the 4 new variables I wanted to introduce, and I'll just quickly go through an example to finish this video off, and then we'll move on to more topics in the next one. Okay. So I have this written up somewhere over here. Right. Well, actually, I've typed it out too. Okay. A car tire rolls with an angular velocity of omega equals 50 radians per second, right? And it has well, the tire has a radius of 0.3 meters. So we want to know what the velocity of the car is, assuming there is no tire slippage, right? So what are we really asking about here? Let me draw a little picture here. Imagine this is our car, and we have some tire. Maybe I'll make the tires, or maybe I'll just make the whole thing a little bigger. So imagine this is our car, and I'll make the tires exaggerated in size here. So imagine these are our tires, and I know they're not quite the same size, sorry about that. But we can imagine that we have a tire here with some radius r, and this tire is going to have, excuse me, this tire is going to have some angular velocity, omega, right? And we're told that omega is 50 radians per second. I'm just going to mute my mic while I cough here for a sec. Excuse me. Right, and right, we're told that the radius is 0.3 meters, right? And we want to find what the velocity of this car is. Well, assuming no tire slippage, so we have this requirement here that the tires are not slipping. Well, then whatever the velocity that the tire is, actually this would be going backward, right? So I need to be careful how I draw this. So we're going to say, let's keep this our omega, but then our velocity, obviously, if we think about this thing hitting the ground, our velocity is going to have to be in this direction, right? But so if our tire is rotating this way and it's not slipping, well, it's touching the ground, right? And so whatever our tangential velocity is with the tire on the ground, that's going to give us the velocity of our car advancing here, right? So really, this is just a question of translating our angular velocity given the radius of our tire into a tangential velocity, right? Because if there's no slipping, the tire is rolling, and the car is moving forward, right? So let's take a look at what equation we might want to use for this. Well, we just generated this v equals r omega, right? So if v equals r omega, if our tangential velocity is equal to our radius times our angular velocity, well, we already have two of those values, so we can just sub in our values. And so we're going to get v equals 0.3 meters times 50 radians per second. And if you do that multiplication, I guess I did some rounding here. What did I do here? Oh no, yeah, okay. Yeah, so if we do that, you're going to find out that v is actually 15 meters per second. And so let's just, again, one more time, think about what's happening here. The tire is rotating with some angular velocity, and it's also sitting on the ground, right? So as it rotates, it's rolling along the ground, and since it's not slipping, the tangential velocity is giving us the velocity of the car, because whatever the velocity of the tire versus the ground is, well, that's the velocity that the car is moving forward with, right? And so that's just a really simple example of how we might use some of these equations that we generated for uniform circular motion.